review from yesterday, if we are multiplying two binomials, how would I do that? How can I multiply these binomials? I can FOIL. Yeah, yesterday we learned we could FOIL. We could use the distributive property. We also had some visuals. We had area model, and we had table. If I were to use FOIL, or distributive property, or even an area model, what am I multiplying? Explain to me how I would multiply it. Where would you begin if you had to multiply this?
I would start by choosing the FOIL, and then if you were FOILing, you would do the 2x, and then times it by the x of the other.
Yeah, so I'm going to take this first term, and I am multiplying it by everything in the second expression. Right? So that's really how it would look if we broke out the distributive property, which would give us what? What would those first two terms be? 2x squared plus 6x. Good. Now that would be the f and the o of FOIL, but if you use the distributive property, it would look like that. And then the second part, I would have to multiply this second term by everything else in the other expression. If you FOILed, that would be representing the I and the L, which would give us what? Negative 5x minus 15. That would be the I of FOIL, and that would be the L. So then at the end, I can combine what I can. Be really careful with those like terms. I would be left with 2x squared plus 1x, good, minus 15. Perfect. Today we're going to take a look at a different type of example when we are multiplying two binomials. So you are making square invitations for a party. You start with a square piece of paper, this white piece of paper, and it has 6-inch sides. Okay, so we see that piece of paper. You are going to cut it, and you're going to actually reduce it by x on each side. Okay? So you see I'm like cutting those pieces off. And we're going to figure out what's the area of the new invitation, the smaller one, because we're going to make it a little bit smaller. What is the length of each side of the invitation after I cut the strip off? What is this?
6 minus x.
6 minus x. It was 6, but then I took away x. Even if I don't know what that is, I can still represent it as 6 minus x. And how about this side? That is also 6 minus x. It was 6 inches. I removed that x sized piece. So I have 6 minus x. If each side of the invitation is 6 minus x, what would I do to find the area? I would multiply. We know whether it's a rectangle or a square, I would multiply both sides, right? The length times the width, okay, to find the area. Okay, so here is our problem. We have 6 minus x squared because we're multiplying 6 minus x times 6 minus x. Okay. Is this the same thing as this? In both examples, am I really just multiplying 6 minus x times another 6 minus x? Yes, so I could show it either way. How would you find the product of that multiplication problem? Okay, so yesterday we talked about 4 methods. If you wanted to use visual, or you wanted to use the distributive property, or if you wanted to FOIL, you know how you can multiply this out. So take a quick second and find what the product would be of those two binomials. Who wants to share what they got? Abraham, what'd you get? 36 minus, just minus x squared?
It's 12.
Did we all get that? Sarah?
I got 36 plus.
Yeah.
36 plus x squared? Did anyone else get something different?
Oh yeah.
Wait, Sarah?
36 minus 12x plus x squared.
If we were to multiply, I'm not just squaring the 6 and squaring the x, because that doesn't represent actually multiplying both binomials by themselves. So these two would not be correct. Take a look at how we would break it down. If we broke it out distributed property or FOIL, or even an area model, if you did an area model, it would not just give you, this here would be the x squared, and this would be the 36, but you would still have negative 6x and negative 6x. You can't forget about those inside terms. So, do you notice a relationship? That is, we learned how to do that yesterday. Don't try to take a shortcut there. If we're still multiplying two binomials, yesterday you learned how to visually do it or algebraically. But sometimes there are ways that you can multiply binomials a little bit quicker. We refer to them as little shortcuts. Okay? When in doubt, you can always use the FOIL method or the distributive property or an area model or a table. But today we're going to talk about multiplying a special case where we're actually squaring the same binomial. A number, two-term binomial, times itself. Sometimes we see it represented like this. Most of the time, we see it represented like this. A binomial times itself, or squared. Okay. So now, look at the trinomial we came up with. Do you notice any type of pattern or relationship between the terms of the trinomial and the terms of the original binomial? Try to find, if you had to make up a rule that was generated from this binomial to that trinomial, what do you think happens in each term? Like, how did we get the first term? How did we get the last term? How did we get the middle term? Eric, what do you think?
36 is the square of 6.
Say again?
36 is the square of 6.
Okay, so this is the first term squared. Do we all see that?
Yeah.
Yeah. Okay, what else? What other patterns do we see, or what other connections? Say again?
All the numbers are squared.
What do you mean?
Like, if you multiply 6x to the second power, it will be negative 10.
6x to the second power.
I mean, to the...
Catch yourself, because you're on the way to finding it. What else can we generalize? What about the third term? What do we notice about the third term in the trinomial? What squared? Where is that in the binomial? Okay, so it's the second term squared. It's okay. For anyone listening, she pointed to the second term of the binomial. Okay, good. So we see the first term, we see the last term. You see where it comes from. What about the term in the middle? Where did we come up with the negative 12?
So back to the area model.
I'm going to show you. If you need to see it on an area, the area model actually shows it perfectly, and it explains why the rule is what it is. How do you think we got it?
First term plus 2.
The first term plus 2 plus x?
Times 2.
The first term times 2 times,
-1.
Times negative 2, right?
Eric, what do you think?
The second. The first term times the second.
The first term times the second term times 2, yeah. I'll show you. Now, I'm going to show you where they come from, okay? I'll show you where they come from. Okay? Now, let's just say we had a different trinomial. We had x squared plus 12x plus 36. what would the first term of the binomial have to have been? An x. What did the last term have to be? A 6. What kind of 6? Positive or negative?
Negative. No, negative. Negative.
For this trinomial. Why positive? What part of the trinomial tells me that it had to be plus 6x and not minus?
Everything in the equation is
What specifically?
Plus 12.
The plus 12. Because, think about this, negative 6 times negative 6 is what kind of 36?
positive.
If you're squaring anything, it's always going to be a positive because negative times a negative is positive and a positive times a positive is a positive. So this is not what's hinting at it, it's this. The fact that that's a plus 12, no term that was multiplied was negative, so all of them had to be positive. Okay. So now let's take a look here. This is considered a special case. We're taking a binomial and we're multiplying it by itself. If we simplified, and this here is an algebraic proof of where this comes from. My first term being an A, my second term being a B. If I FOILed, I would multiply the first term by itself. That's where we're getting this A. If I go all the way through FOIL, the last term, the L, is represented by the last two terms, which just so happen to be the same thing. That's where I'm getting the L, that last term squared. The O and the I, the middle, is where we see what? What do you notice happens when you multiply the outside, A times B, and then the two insides, which are essentially another A times B? How many of them do you have? I have two. This would be the O, and this would be the I. That's where the 2 is coming from, because really you're multiplying those, but then you have 2 of them. So that's why we can double. If you need to see it in an area model, this tends to be very clear for certain people. If I have A times B times A times B, that first term squared is represented by A squared. The second term squared is represented by B squared, but I'm still getting these two rectangles, both of which have the same size, which is where that 2AB comes from. Right. What? So if you ever needed, or felt like you could square a binomial faster, your pattern would be this. It's going to be broken out more on the next slide, for those of you that are writing. The square of a binomial is the square of the first term plus double or twice the product of the two terms in the binomial plus the square of the last term. There are two examples there. You don't have to write the algebraic examples. The actual examples here might be better. Notice the difference between the binomial that has a positive 4 and what it does to the trinomial, and the binomial that has a negative 3 and what it does to the trinomial. Now, you will not be forced to use this strategy if you were squaring a binomial. If you had x plus 4 squared, you could always represent it as x plus 4 times x plus 4 and actually break it out and FOIL or use distributive property or use an area model. It would be up to you. There might be times where something that helps you get through the multiplication faster may come in handy. And that would be if the ultimate question wasn't for you to find the trinomial. So we're going to look at an example next where we need to figure out the value of that trinomial, but it's not the answer to our question. We need to take it a step further. And you'll notice that as you start to go steps further, the problems become longer and longer to do. So having little ways to shortcut comes in handy. Is anyone still writing? Okay. If you have one of the examples written, that's good. You don't need to have both. If you don't want to.
Okay. Are you recording?
Help! She's gonna kidnap us. Help us! Please help us. She's torturing us. Who is a bad man? Help us! Save us!
I saw that. And I will not say in front of everyone that you just missed your mouth when you poured the water in the Oh, I'm listening to this video now.
Oh, she was doing that.
Yeah, because I was doing the third chorus and then they started laughing. And I just wanted to try.
Wow,
I
Paige
understand.
Torres know how to drink from a water bottle.
Okay, so let's check out this example. This is a time where it might actually be pretty helpful to have some way of going a little quicker through squaring a binomial. A square outdoor patio is surrounded by a brick walkway. So the dark red is the walkway, and then the patio is like the tan with the lines through it. We're going to find the area of just the walkway. What?
are those other measurements on the outside? The x plus 6 thing, what is that?
Where do you think that came from?
The total?
How?
I don't know.
Where did the x plus 6 come from?
Because half of it is 3.
Yeah.
On the other half.
That is represented by what value?
3 or x.
This is x. And what's this? 3. And what's this? 3. So what is it total? This is the x, but then we have 3 here and 3 here, so we have 6. I think I actually deleted a slide. So our entire thing here is x plus 6. Now question, if I needed to find just the walkway, what would I do to find the area of just the red walkway?
You would find the area of the tan and then subtract that from the entire thing.
Okay, so I can find the area of the tan patio, and I can subtract that away from the area of the entire big square that I have. Okay, good. So let's try that. I don't know how, but I ended up skipping those 2. The area of the patio, if you notice, this is a square-shaped patio, and we know that the width here is x, the length here is also x. We could represent this area as what? X squared. How would we find the area of the whole thing? We're really multiplying x plus 6 times itself. So using a newer strategy, how could you get the trinomial that is represented by this? What would the terms be of my trinomial? X squared, which is 36. Where would that go? Good. What's the middle term? Where'd you get 12x?
We multiply the 2 terms.
Yes, 6 times x, which is 6x, and then times 2. Now that was a little bit faster than saying x squared plus 6x plus 6x plus 36, combine like terms, and here we are, okay? Now, using this strategy here was a little bit quicker. Why might that matter? Is that the answer to our question? No, that's only part of it. What do we need to do now? Like Patrick said, we have the area of the whole thing. We know the area of the patio. What's the area of just the red walkway? Say louder. 12x plus 36. How did you get that? Yeah, if this was your whole thing, and then you took away the x squared, you're left with 12x plus 36. That example it didn't take that long, but you may start to see some examples that are a little beefier. If you can go through squaring that binomial in a quicker way, it may help. You don't have to. I'm not going to ask you specifically on a test. Use the strategy we learned for squaring a binomial. You can always break it out in FOIL, distributive property, area model, table, whatever you feel most comfortable with. But this doesn't just help with variables and constants. We can actually use the same strategy to multiply large numbers mentally. So we are going to find 39 squared, and we're going to do it in our heads. So I don't want you to have, you're not writing anything down. Okay, if you're going to hold a pencil, that's fine, you're not going to write it down. Okay, we know that there is a strategy for multiplying binomials times themselves. Right? We know first term squared, last term squared. The middle term there is 2 times first term times second. Okay, squaring the number 39 is challenging. Is there a way we could rewrite the number 39 so that it's actually a binomial?
Oh, I did that in my head.
What did you do?
I separated it.
Into what?
30 and then just 9.
Is there another way that we could separate 39? That, think about this, each number you have to be able to multiply it into 10. You could also go bigger and take something away to get to 39.
30 plus 3 plus.
We're looking for a binomial.
Oh, fine.
40 minus 1.
You can do 40 minus 1 as well. Now, if you were to multiply this number squared, what would you need to do? There's 3 things we would do, right? What do we do when we square a binomial? Square the first term, square the last term,
And then multiply.
and then multiply the 2 terms, and
by 2.
then multiply by 2. Could you do that in your head for that?
Yes.
Try it. If you need to talk it out to yourself, that's okay. Just try to talk a little bit lower. I know for me, like, I need to multiply out loud. Oh my god, I forgot my first number.
Oh, I was writing Grande Volta to Team.
Oh my god. I forgot my first number.
Go now. Go now. So if you're gonna give,
Oh.
I'll let you write down your answer, but not the words to it.
I can't help it. I like to write things.
Go ahead.
Same drive.
Anyone have a number? David, what do you have? 1740. Which way did you use?
30.
Okay, so I'm going to separate it. Okay, who else has something? If you've never done this before, don't worry if you're wrong. What do you think? Did you catch a mistake? I'll come back to you. Check it out. Which one did you use?
30 plus 9.
Who else? 342. Which way did you use? 342. Anybody else?
I know what I did
81.
wrong.
Which one did you use? Okay. Who else?
We don't know. I
Anyone
know I
else?
did wrong.
Say it again. Which way did you use? 1,518. Which way did you use? Left or right? Anybody else? Before we, I don't know. 1,600. 1,000. Which way did you use?
680.
The second.
No, it's
1604.
Yeah.
Okay.
680.
681. Which method did you use? 11. 681.
I'm reading 171.
170. Which way do you? Am I changing this one?
No.
Okay. 999. Which way do you use? Now, in order to do this in your head, it's really important that you can calculate pretty fluently both numbers. Okay. So, and it really depends. The most common mistake I found was the middle term of the trinomial. Students were just adding the numbers together, and we're ending up with like 39 times 2. It wouldn't be 39 times 2. It would be 270 times 2 because it would be 30 times 9. Okay. For those of you that got closest, the ones on the right. Okay. 40 times 40 is 1600. Negative 1 times negative 1 is 1, so you have 1601. 40 times negative 1 is just minus 40. So from 1601, I can take away 40, which would give me what? 1500.
21.
If I take away 40 and then another 40, I'll be left with 1621. Let's see if we got it. 1500. Oh, I was off by the 15. Okay. So we had the 1600 and the 1, 1601, and then you can subtract 80. Minus 80 would have been the 1521. So again, not something that you're going to be required to do in your life. But this is a way that breaking out something into a binomial and using that strategy, you can actually multiply large numbers times themselves. If you've ever seen, there's a TED Talk, there's a guy named Art Benjamin, he's a college professor, he's a mathematician. He squares like crazy big numbers in his head. This is actually the strategy that he uses. He breaks up the numbers into numbers he can easily calculate, squares them all, multiplies them all, and then adds it all back together. There's a really cool video of him, maybe I'll show you at some point. Okay, so now we're going to practice. We're going to skip that. We're going to go to this. I'm going to pause the video, and I'll explain to you what we're doing. Oh.